Hello guys, and welcome back to ChatCraft. When last time I was talking about the matrix argument, and this time I thought I might talk a little bit about science and the scientific method, because I have seen in the last few days that it doesn't seem to be that clear to a lot of people what the scientific method actually means. Like what science is and what it does. One of the most common things one of the more common things, misunderstandings I've seen is that people say science is the process of collecting and proving statements about nature. It's not it's not that far off from the truth, but it shows one really big problem with the understanding of science, and that is that science does not attempt to prove anything. Science doesn't have the capacity to prove anything. If you want proof in anything, the only discipline of, well, human learning that provides proof is mathematics. And I'm not just saying that because I am a mathematician. Nowhere else can you find strict evidence. Unless maybe if you're taking philosophy or something in as being something where evidence is actually done. I would say that philosophy doesn't even try to have evidence for anything. It's mostly, if I say mostly talking, it sounds negative. I don't mean it in a negative way, but it's not really a discipline that tries to prove things, to my mind. But yeah, the reason you can prove things in mathematics, of course, is that you go ahead and you define your parameters. You basically define the universe you're working in. And then if you have that defined rigidly, you can prove things based on those definitions. But in science, particularly, you don't have the liberty of making up your universe. You have to go with basically go with what you're given. So let me just make a few bits of charcoal, because I will get tons of jungle wood, and I think I might have to, I might want to smelt a lot of my cobblestone into smooth stone. And that chicken is still alive, of course. Yeah, I was actually going to do some smelting, so I'll need a second oven, furnace, of course. We'll need this and half of this, and that should be fine. There we go. So yeah, talking about science, I guess general misconception is that science proves things. Which I would say it's understandable that people believe that, but that obviously doesn't make it true. Science is not so much the attempt. Well, it is an attempt. It's an attempt to find truth. But science doesn't, or at least shouldn't, claim to have truth, basically. So someone telling you he's looking for truth, that would be a scientific statement to make. You're looking for the truth. But someone telling you he has the truth, that's a religious statement to make. And as I said, the problem is that science has to take the universe as we have it, basically, We live in a certain universe, and that's what we have to go with. Which means that we can't change things to be, I don't know, like we want them to be. They are as they are, and we have to deal with that and try and make sense of that. But it's always there's bound to be mistakes, just because of the limitations of what we have to go on. We only have our universe, and that is, with all its randomness and inexplicable or difficult to explain things, you just can't have proper evidence in this universe. Well, proper proof, I'd say. So what science, or the scientific process is you have this universe around you, this whole gigantic universe full of things you don't understand, and you try to make sense of it. So you're looking for the truth, but at the same time you accept that you're never actually going to find it. But anyway, big universe, all those phenomenons, all those cool things you see, even mundane things. Why do things drop why do they fall when you let go of them? Why do we have tides? All that kind of thing. And we try to explain those things. And of course, an explanation that was quite common actually back in the days, thousands of years ago, would be that some sort of outside force, some divine creator, some god, made those things. Like in ancient times, that would be the way to go. Why do we have tides? Because the sea god makes them. Stuff like that. I believe the question why things fall down just hasn't really been asked that much, but why do we have rainbows? Because the sky god is building a bridge. What's the sun? It's the flame god riding through the sky. Stuff like that. And you couldn't really prove that wrong as such. At least back in the days, they had no means of doing that. But the problem is, it's not a very useful explanation. You're just saying because, instead of giving an actual reason. So that's where science kind of came into the whole process, and people weren't happy with the explanation of the sun god riding through the sky. They weren't happy with the explanation of the water god making the tides. So they had to come up with other theories. Stuff like the tides are actually caused by gravitational pull of the moon. And that makes you... well, I guess that's a superior theory, and that's all it is. The fact that the tides are caused by the moon is a scientific theory. Nothing more. The advantage of that theory is it allows you to make predictions. And these are halfway done. Fair enough. And that's one of the really, really important things about scientific theories. You can make predictions based on them. So, for example, if the moon is the cause for the tides, and we know that at times or rather the gravitational pull from the moon is the cause for the tides, we know those gravitational forces can vary depending on the position of the moon and Earth's rotation and such. So we would expect, for example, tides to be stronger and weaker at times. We would expect certain tides to be particularly high at particular moments, when we expect the gravitational pull to be particularly strong. So, for example, you could predict that on some date we would expect tides to be a lot higher than on some other date, and we could be fairly specific about that. And then when we basically observe the tides on those days, we find out that we've been right, so our predictions have been correct, which shows that our theory is quite strong, because it's made certain predictions which are correct. On the other hand, it is also in a sense a falsifiable theory. Simply because, for example, if you have another planet, maybe, which also has water on it, which we haven't found, but just hypothetically, which doesn't have a moon, you wouldn't expect tides on that planet, because those would be caused by a moon, and if the planet doesn't have one, there wouldn't be tides. Maybe there would be something a lot weaker from gravitational pull from a sun, if that planet were orbiting a sun, for example. But we would just expect tides to be very, very different in particular ways. So we could also falsify that theory, because if another planet had water on it, and also had tides without having a moon, we know it can't really be the moon if that's not the way it works. And that's the way, that's just the way science works in trying to work out the truth. They observed certain things, like the tides, like stuff falling down, and then they formulate a theory, which they try to use that to explain things. And from that theory, they devise new experiments to basically falsify or test that theory. Very good example, which I know is slightly problematic because of religious views, but look at the theory of evolution in biology, and probably people will comment saying that they don't believe in it, which is rubbish, but anyway. So Darwin went out to the Galapagos Islands back in the days, long ago, and he saw all these finches. Well, he saw all these birds with very different beak shapes, so he thought, cool, all of these different birds, I'm just going to kind of analyze them. I'm not certain either. I don't think he took any home with himself, but he made drawings and all that. And then he asked a bird expert if he could classify those birds, and the bird expert came to the conclusion that they were all finches, with massively different beak shapes and size differences and such. And all the finches that had been known until that day were rather similar. So these were, well, they were finches in terms of their structure and just how a finch is defined in biology, basically. They were very different from the finches that were known. So, from that, he just had to find a reason for that. Because, for example, one of those finches would have a beak like a woodpecker, but it wasn't a woodpecker. He just looked very similar in terms of beak shape. And the predominant theory at the time was, of course, that someone had made the beak of the woodpecker so he could peck wood to search for larvae and insects living underneath the bark and such. But the question is, if he already had the woodpecker, whoever supposedly designed things, why would he then make a finch having the same beak shape if he already had the woodpecker? Or if he already had the finch, why make the woodpecker? So that struck Darwin as being strange. He hadn't expected that, basically. So he came up with that theory of evolution, which basically states that nature just has to go with what it has. There were no woodpeckers that came to the okay, I need 16 for each of those furnaces. There just were no woodpeckers which happened to migrate to the Galapagos Islands. What did happen to migrate there were some finches. So that's really all that nature could work with. So those finches at first might have struggled living there, but since they didn't make a conscious decision to fly somewhere else and settle there, they didn't have much of a concept of, okay, this is going to work, we're flying back to the mainland. They were basically stuck there, so over time they slowly changed. And the reason the Galapagos Islands are so important for this is because they're a series of islands which were probably populated at first by the same finches, but then the local finch populations, they basically diverged from each other, changing because the islands were different. Because I believe that basically the islands didn't have much of an exchange between them in terms of plant material, for example. So certain types of plant might be very common on one island and very uncommon on another. So a bird specializing in that plant would be successful on that one island, but because the plant is really rare on the other, he would struggle there, because his main food source is not as abundant. I don't have much oak wood. I really should have more oak wood. So, sapling time. And just from that first initial bunch of finches, for example, these diversified, because on the one island there was a large amount of certain plants that produced rather large seeds, or maybe the island had a river which dried out, so in general the climate on the island became drier and plants made bigger seeds, and so in turn the finches had to develop bigger beaks. Perhaps on another island there wasn't as much there weren't as many seeds which were really edible for the birds, so they had to focus on eating insects, and so they would develop the woodpecker beak to get at the insects underneath the bark. And that's just kind of the way it diversified. And Darwin came up with that theory, which in itself was just that. But the reason it was such a good theory was that it was able to predict so many things. The whole theory of common ancestry, for example, predicts that the core biological functions would be very similar in all animals, like the way DNA works. You would expect that to be very similar in all kinds of life, basically, and that does happen. So the predictions that were made by the theory just happened to be right, and that's really what makes a theory really great. Like the theory of gravitation at first, it predicted a certain type of movement of planets, because we'd observed, I think, all the planets up to, I don't know, I think we had 6 planets that people knew about, astronomers knew about. And so the theory of gravitation supposedly would have to explain why these planets orbit the way they do. And it didn't work out. If you just applied the gravitational laws as they had been established, the solar system wouldn't have worked the way it does. So what really saved the theory, kind of, was the fact that we discovered some more planets which fixed those problems. And the point was, the gravitational these laws of gravitation actually predicted there would have to be another planet orbiting at a certain distance in a certain speed to make the whole system work out. So that's really one of the great strengths of a scientific theory, that you are able to predict things about nature. But never ever should a scientist say that he's proven something. All you do is find evidence for it. But the evidence could be explained by a different theory. Like, at first you find the evidence of there being a sun in the sky. So your conclusion is that's the fire god riding across the sky. for all the observations you have at the moment, that is a legitimate theory. It explains everything you've seen. It just doesn't predict anything. And as new data emerges, the fact that the sun is a star, gigantic helium hydrogen fusion bomb constantly exploding in the sky, kind of contradicts the flame god theory. So you have to move on to a different theory. But the point is, that could still be a wrong theory. Maybe something else emerges now, which shows us that really, I don't know, it's the exhaust pipe of a gigantic spacecraft, whatever. Just making stuff up here, of course. There's no evidence for that theory at all. But the point is, you don't know if your current theory is right. You can just evaluate its value, which sounds strange, but I guess that's where the word comes from, really. You can assess its value based on how accurate it describes the world around you. Which is why, and that's actually a problem in, for example, in current cutting-edge physics, like the string theory stuff and such, and quantum mechanics. The predictions made by those explanations can sometimes be off by a lot. So as those theories stand right now, like quantum theory, they're not very good. Like they have a lot of issues in the details where they would predict something to be a certain size or a certain time, and in reality we get results that are vastly different. So that's a theory which does still take development, basically. It doesn't mean it's wrong or that it's bad science or whatever. It's a good theory and explains lots of things, but it tends to be the way that science works, that you're constantly improving your knowledge, and you're constantly reassessing things you know, and you're constantly having to change explanations for these things. And that's, I guess the phrase is that science is a self-correcting process. So you find out something new, and you have to go through a peer review process with this. So you can't just say, this is what I found out, so this is now true. The way it works is you have to publish those results, and all the other scientists can look at those things and say, okay, that seems to be reasonable, or they could point out mistakes you made in your experiment, like you forgot to account for the fact that the satellite is moving, so your results are wrong, stuff like that. And when a fact has gone through the entire process of pretty much every other scientist in the world looking at it and saying, that's fine, and if most scientists agree that it's correct, only then does it get accepted, and you will have to incorporate it into your new theories. Which is a very, I guess it's a very strong process to find the truth. Because of so many people having to agree that it's correct. It's not one person publishing something and then it's true. It has to be almost the entire scientific community has to agree with a certain fact before it can be called a fact, or before it can be called a valid scientific theory. So yeah, just smelting stuff, by the way, for a possible house, maybe, I don't know. And all in all, I guess that's a very small part of what science is about, but basically science isn't really designed to prove things. It's designed to find evidence and explanations for things and trying to quest for the truth, but basically there's an awareness that it cannot be found. And that does not only apply to the theories I mentioned, like quantum theory and theory of evolution. The way scientists see it now, the theory of evolution is actually the single most supported theory in science ever. So what I'm saying applies more so even to like the atomic theory of atoms being what elements are, what molecules are made of, and molecules being what matter is, what stuff is made of, atoms are made of smaller things still. That's just as much a theory which is still constantly being developed, because in general the big points don't change, like the fact that atoms contain protons, electrons, neutrons. But the details tend to change, like what do protons consist of then, and what do those things consist of, and all those things. So science is a constantly self-correcting process, attempting to find the truth, but being aware that it can never quite find it. So I'll see you next time. Bye bye.